Good afternoon. Dear students, can you hear me?
Yes, we can.
Okay, thank you very much. Okay, thank you. So then we will continue today with theory of machines. Let's share the slides. So what did we discuss finally in our last lessons? Can you remember? So we were talking about the mechanism and kinematic model. So we said we will deal mainly with geometry, and therefore you have to well prepared for the geometry. We will use compass, we will use protractor, ruler, and so on. And you need also in the in the exams. And we discussed the types of member of the mechanism. That means the links and binary, ternary link, and quaternary link, which we use in the mechanisms. And we said there are in space, a normal object has 6 degree of freedom, 3 translation and 3 rotation, as you see here in this picture. So as you know, we have 3D space, and in 3D space, mainly any object can have 6 degree of freedom. That means 6 degree of freedom. 3 of them is the translation along X, Y, and Z axis. 3 are rotation around the Z axis, X axis, and Y axis, and so on. So based on the reality, in the mechanism we use in the machines has also consists of also some links, and links are connected via the joint. And we said joint and joints are also important regarding the degree of freedom. So you see here the revolute joint, 1 degree of freedom. This is the rotation.
If you are sharing slides, we cannot see anything.
You cannot see that?
No.
Oh, sorry. Okay, so let's come back. Share the slides. Thank you that you remember. Sometimes was okay. So can you see now? Yet?
Yes.
Okay, good. Thank you. So thank you for remembering, because sometimes I forget it. But you know, there's different possibilities if we use the OLearn platform. But in this case, if we use slides, we have to share the screen, the actual screen. Okay, we said generally any object has 6 degree of freedom, like this 3D system is showing. So usually we have 3 axes to define the its position of any object in the space, and 3 axis, that means the x, y, z axis. And any object in space can move, move in x direction or y direction or z direction. That means 3 translation. And also the other possibilities that the object can also rotate around z-axis, x-axis, and y-axis and x-axis. So 3 rotation and 3 translation, in total 6 degree of freedom if there is no contact. If the object has no contact in the space. But in machine, we use the mechanism, and mechanisms are they consist of links, and links are connected by joints. So the joints are important now to check regarding the degree of freedom. So here we have a revolute joint. We already mentioned before in our last lessons. More or less it's repeating. So revolute joint, there is only one rotation, but rotation around this axis here. So around this axis, there is a rotation around this axis like this. So delta theta. So this is the rotation, and therefore we call it revolute joint. And the other is, here prismatic joint. So it has a translation. Undergoes a translation like this, or in that direction, and like shown in the x delta x. So here the rotation, and here we have the translation, and here we have the rotation, helical joint we call that. Also 1 degree of freedom. But here in that case we have a translation. Let's use the laser pointers. If you have such a joint, we have a translation rotation together. That means this type of joint has 2 degree of freedom. And here we have the spherical joint, and spherical joint has also, 3 has 3 degree of freedom, and all of them are rotation, like around the x, y, z axis, but there is no translation since it is a spherical joint. So if you have such a joint, that means 2 components are in contact. You see this one and this one, the red one and the ground one. And you see this, the red part can fulfill 3 motion. 2 of them is translation, like delta y and delta x, and the next one is the rotation around the, let's say, around the z-axis. We can say, we can indicate that. So this is could be, and the z-axis like this here around the z-axis, and this is the x-axis here in that direction. This is the x, and this direction is the y-axis. So in x and z-axis, in x and y-axis we have translation, and around the z-axis we have rotation. So, okay, then you see here some members or links joined together. Here we have 2 member or 2 links are joined here. So there is a pin connection and has 1 degree of freedom. And this is 1 degree of freedom is the rotation, as you see, like indicated here with delta theta. And here also 2 members are connected to links are connected, joined. So, and this has such a motion. That means translation along x-axis. And Here we have rotation and translation at the same time. That means 2 degrees of freedom. And here we have also translation and rotation, and also 2 degrees of freedoms. And here in that case we have here the rotation, and here we have the rotation and rotation, so 2 degrees of freedoms, and here 1 degree of freedom, as you see here. And in that case, and in this example, so we have on the rotation, here the rotation, but if the rotation is also involved in the translation, then we have 2 degrees of freedom. But if it is only rotation, then it's only 1 degree of freedom. I mean, if there is a motion in that direction, so we have the rotation and translation at the same, therefore we can say 2 degrees of freedom. Or if it is a higher pair, that means the contacts are like curved. So we call these type of contacts like this higher pair. So there is no exact joint. So therefore, these type of connections or joints we consider 2 degrees of freedom if we have such a connections. We will talk later about. So then the links. So let's talk a little bit about the links. Links are the binary links and the ternary links. As you see here, quaternary link, that means a connection in 2 points, and here 3 and here 4. And this means the moving rotation joint. This is the moving rotation joint here, so like this. And this is the grounded rotation joint. So you see here, this means the grounded, this is rotation, this is the rotation, this is grounded. This is moving translating joint. That means motion in that direction. So moving translating joint. So this is also grounded translating joint. Grounded, so this means ground. So fix, that means ground fix. Grounded translating joint. And here we have grounded half joint. Like this here, grounded against. So this always means grounded, grounded half joint. And moving half joint, so 2 degrees of freedom here. Also here 2 degrees of freedom if we have only this part. So now we have here an example, you see, and this is, you see, binary link, and this is ternary link, and this is also ternary link. And here we have 2 degrees of freedom, and here we have grounded joint, grounded rotating joint, 1 degree of freedom. Here also 1 degree of freedom, 1 degree of freedom, 1 degree of freedom, and here also 1 degree of freedom, and here also 1 degree of freedom, because this is the rotation and this is translation. So then here we have, since we have three members connected, we have here 2 times 1 degree of freedom, 2 times 1 degree of freedom. And here we have 1 degree of freedom, slide. And here we have 1 degree of freedom, grounded rotating joint. And here we have 2 because it's a higher pair. And here we have 1 degree of freedom. This is the grounded rotating joint, and so on. So why we are talking about? Because later we have to analyze the mechanism. and we have to build using the mechanism. We have to build the kinematic model, and then we have to analyze whether analyze about the degree of freedom. So you see here there's a mechanism, a weight training mechanism, and in this mechanism there are many members involved here, and all the members are here defined L1, L2, and L3, and so on. And this is, you know, we can not we cannot really maybe at one break we cannot see everything, but if we create using this mechanism a kinematic diagram, and you see in this kinematic diagram all the grounded rotating joints and all the links, and is it binary or ternary or quaternary, and the joints, is it as rotating joint or translating joint, sliding joint, and so on. So open and closed mechanism chain is this we call open mechanism chain, because it's not grounded. Here this is grounded, but it's not grounded. So we can say, if we use the column like it seems like this. So this is the grounded one here. Okay, and this is this one, and this is the next one. So it is open mechanism, open chain, kinematic chain. And he is closed because, you know, all of them are fixed. Let's draw here the same as kinematic chain like this. So this is grounded. This is also grounded. So, and the grounded part. Okay, so this is open, this is closed. If one of the member is not joined and connected, then we say this is open mechanism or open kinematic change, like robot. You know, many robots we have, and you have seen, you know that, and this type of mechanism, robot has an open mechanism, open chain, or mechanism chain. Okay, so then let's talk about the planar motion. So this is very important what I'm saying now. So planar motion, that means we are going to analyze the motion which occurs on the plane. So this is also actually planar motion. This is a planar motion on the plane, on the X, Y, Z. Planar means we have here the X, and here we have Y-axis. 2D motion. We learn already in dynamic. So, so and here's two links, 1, 2, and they are all of them. I mean, all this on the plane. How many degree of freedom they can undergo? This, for example, can rotate around this axis, or can move in X direction and Y direction. So 3 motion can be executed by this member, and also by this member 3 motions. But if they connected together, I mean, here you see by pin, or the pin joint or revolute joint. So then we have one rotation, another one rotation, and X, Y, and the translation in X and Y direction. So these two members have actually in general 6 degrees of freedom, but if we connect them together, join together as a revolute joint, so then the 2 degrees of freedom reduced. That means there is only 2 rotation and 2 translation possible. So in this example, you see there is 5 degrees of freedom, because this move in X direction, Y direction, and this also can move in X direction, but additionally they can rotate, and this can rotate, and this also can rotate. So therefore, we have here 5 degrees of freedom. So as far as I remember, we discussed also this part, so more or less is repeating. So calculation of degree of freedom now the important topic. So we have we talked about the joints and links and members also, and then now we are coming to the mechanism. So mechanism like 4-bar mechanism consists of 4 link like this. Let's say this is the one, and here. So, and this is the small link, and this is a little bit longer, and we have here this other one. So let's say if we drive this link in that direction, so counterclockwise like this, so you can easily imagine this is theta. So if we drive the member, let's say the member 2, this is the member 2, and this is member 3, and this is the member 4 or link 4. So, and this is 1 we have fixed. Actually, this is a kinematic model or mechanism, but if we sorry. We will discuss later, but now I think it is good that we that mention it. So if we draft this one, the mechanism in that way, without fixing, without grounding, so without grounding. So this is this is member 2, this is member 1, and this is member 3, and this is member 4. That means 4-bar mechanism consists of 4 bar, and the joints are revolute joints, pin joints. So if we fix one of them, like 1, if we fix one of them, so then we have a mechanism. This is not a kinematic chain anymore. Then it is a mechanism like this. But if we don't fix any one of them, it's a chain, kinematic chain. So that means we can fix 2. We can ground the member 1 or 2 or 3 or 4. We are free. So and therefore, kinematic chain give us many possibilities. That means that as much as possibilities, as much as it is the number of the links give us possibilities to create another mechanism. Let's say regarding the properties of the mechanism. So if we have such a mechanism, we are interested to know, does it move or doesn't it move, or I mean what is the degree of freedom of the system now, of the mechanism? Degree of freedom of the mechanism here like this. We are not talking about a joint, a revolute joint or prismatic joint or higher order joint and so on. We are talking about the system. That means about the mechanism and degree of freedom of mechanism. So you can easily understand that if we drive this part, for example, here, this we call crank if we drive it. If we rotate like this here, rotate around like this, you can easily see. And this also moves. This part will also will be in motion, and this is also in motion. So this maybe will move to limit position like this, and like this here in between. And this move also like this, huh? Okay. That means, sorry, that means, so what is the degree of freedom of the mechanism? If it is 1 degree of freedom, that means if we apply the motion, one of the members, so the whole mechanism starts to move, so undergoes the motion. And in order to check it, we have such an equation here. You see these equations. This is for the planar mechanism. So F is equal 3 times n number of the links minus 1 in bracket minus 2 times G, that means the link, primary link, and minus link higher order. And this we have to check. If F is 1, constraint mechanism, that means mechanism fulfill the motion. If is less than 1, locked mechanism, that means there is no motion possible. Any of members of the mechanism cannot move. So in case that we have such a connection, that means three links are connected at the same joint. So then the degree of freedom is 2. The connected 2 links, so the pin joint, so connects to. This is the degree of freedom is when 3 links must be joined by 2 joints like this. So one connects link 2 to 3, and the other connects link 3 to 4. So therefore, all 3 links are joined. So then the degree of freedom is 2. So let's have an example. Draw the kinematic diagram. Calculate the mobility. That means the degree of freedom. So you see, there is a there's a mechanism here. And we have to, so we have to draw the kinematic diagram, and we have to check regarding the mobility. That means the degree of freedom of the mechanism. So you can easily follow that. There is a linear actuator here, hydraulic or pneumatic actuator here. So there is a linear motion, and there is a joint here. This is the pin joint or revolute joint. There's another joint here, we don't see that. And another joint we have here. So it seems like this. So we have here joint, pin joint, like this. Okay. and maybe this is like this here, huh? So and there is another joint here. So if this is a this is a linear motion here. So if it moves in that direction, so you can see this is point. Let's say this point. This is A, B, and this is C. And if it moves in that direction, so you can see goes in that direction. So then we can move this part AB up and down using this linear actuator. So then we have to also now calculate the mobility. This is the mechanism, the mobility we have to calculate. So how many links we have, and how many joints we have, and what are the, so we should know how many link we have, okay, for that, and how many joint primary and how many joint higher pair. So then we can write our equations. F is equal 3 times n minus 1 minus 3 times, sorry, 2 times. I made a mistake. So 2 times joint primary and minus joint higher order. So what do you mean? How many links we have here? So this is 1. And this is 2. And this is, we have here this is also, since we have the slider, we have here, this must be 3 and this must be 4. And we have here 1, 2, 3, 4, 4 primary joint and 4 primary joint, and the 4 links. That means this equal 3 times 4 minus 1 minus 2 times 4 joint primary times 4, and there is no joint higher order. This is 0. So then it is equal here 9 minus 8, so is equal 1. That means F is equal 1. So if F is equal 1, 1 degree of freedom, that means, so So the constraint mechanism, it moves. Huh? So and we have the solution here. Of course, we can replace this the linear actuator with those solution. So we have a slider motion, and you see this is 1 and 2 and 3 and 4. So this 4, n is 4, and the primary joints are also 1, 2, 3, 4. This is sliding here, 4. So joint higher order is not 0, and degree of freedom is 3 times n minus 1, minus 2 times joint primary minus joint higher order. So then we have F is equal 1. So F is equal 1. Sorry. Okay. So let's have another example. You know this mechanism, I'm sure you have seen that somewhere. So lift table, there's a table here. So, and the table is going up and down, parallel to the surface. This is also important, huh? Parallel to the surface, going. So here, going up and down. So, okay, let's draw the mechanism. First, the kinematic diagram. We need first the kinematic diagram. So how can we do that? So you see we have here slider like this. So let's have this one and so on. We have here slider and joint here pin joint, here slider and pin joint, and here we have the pin joint, and here we have slider, for example. Huh? So any idea? Okay. So it seems like this. We have here as we have already seen, we have here the slider and pin joint. That's the prismatic and pin joint. And here we have prismatic and pin joint at the same time. And here we have pin joint. And here we have also pin joint. Or so let's write here. We have the degree of freedom. Here we have 1. And here we have also 1. This rotation here, the rotation here. And here we have sliding 1. And here we have also rotation 1. And here we have sliding 1 and the rotation 1. And here we have this is grounded. So this is grounded. So grounded means here, huh? This is grounded. So this is also 1 degree of freedom here, pin joint. So how much in total? 1, 2, 3, 4, 5, 6, 7. So 7 joint primary. 7th primary joint. So let's check the links. So how many links we have? We have one here. This is the one. Let's use another color. Here, this one. Okay, this is the one. Okay, this is, let's say, 2, and this is 3, and this is 4, and this is 5. Sorry, 5, and this is 6. 6 member or 6 link. So then, using these equations, it's a higher order. We have no joint higher order. So if we put in these equations, so 3 times 6 minus 1, so, and then minus 2 times 7, 7 minus 0. So here we have 5, 15. 15 minus 14, as you see here, is equal 1. So then we have degree of freedom for this mechanism. F is equal 1. This is constraint mechanism. So it works. That means if we derive one of them, if we select one of them as driver, usually we select this one here. So as you see here in this mechanism, we select this one as driver. This one by a screw mechanism. So then it moves left and right in that direction, and then by applying this linear motion on this joint for the member, for this member, then the total mechanism can move up and down. Okay. So let's have a break, 15 minutes, and after break, 10 minutes, sorry, 10 minutes. After break, we meet again. Huh? At 2, we will meet.
Okay. Thank you, Professor.
You are welcome.
Sorry, Professor.
Yes?
I wanted to ask one question about the ones we solved right now. It is about the N and the JP. I get the JP is 7 because we counted the joints and the reverse. But the N, how did we get the 6 exactly?
You mean this one?
Yes.
Okay. So let's check it once more. So you have difficulty with joints or links?
The links.
Okay. So links, one is the ground. Here you see. Okay.
Oh, okay, understood.
This is ground, huh? This is ground because
I
fixed.
get it.
We have to fix to the ground. So we need a member or link to fix the mechanism somewhere, and
Oh,
that we call grounded, huh?
I got it. Thank you.
Okay, you are welcome. So can we start now? Can you see the slides?
Yes, Professor.
Okay, so let's start. So we actually finished this example, kinematic diagram. Now we learned what is link and what is joint and what is primary joint and what is joint higher order and what is degree of freedom and what is degree of freedom of a mechanism and so on. Now let's continue with 4-bar mechanism. So the 4-bar mechanism, very famous in this lecture, and 4-bar mechanism, that means the mechanism consists of 4 members, 4 bars. So a linkage with 4 links connected by 4 pins. So this is the main meaning actually. So here we have we call this first one the grounded one, and it's also one. That means this link is grounded linked, as I explained before. So normally it is driven by pneumatic by kinematic chain. A kinematic chain for bar mechanism is like this. I have already shown. So this is the kinematic chain of 4-bar mechanism, like this. 4 links or 4 bar. This is 2, and this is 3, and this is 4, and this is 1. 1. So if we fix the member 1 or link 1, so we achieve such a mechanism you see here. So in this mechanism here, in this mechanism here, the member 1 or link 1 is fixed, grounded. So therefore we have such a mechanism. So this is very important to understand from the basics. So you can imagine now, if we fix, let's write the number of the others also. So this is driver, we call driver. This is the link 2, and this is link 3, and this is link 4. Therefore 4-bar mechanism. Okay, and if we fixed, for example, the member 2, if we fix the member 2, then we will member 2, let's use another color. If we fix the member 2, then we will have such a mechanism. So like this, member 2. They are going to fix it, to ground it. So, and then you see, this is another mechanism. It's not the same. This is not the same. Therefore, it is very important which one is grounded. So this mechanism is not the same with this one, because we fix the, let's write also the number. Here this is 2. 2 is grounded, but normally the grounded one we number with we use the number 1 for the grounded one. Okay, but here for the example, as an example, I write here 2, and this is 1, and this is 4, and this was 3. But normally, for the grounded member, we used 1. So this is not correct what I did here. But I want to show you, if we change the grounded member, we have another mechanism. So, and a different mechanism. So, but please pay attention for that. We used for the grounded one, we used the 1. That means here this is the 1 and this is 1, and this is, as could be 2 and 3 and 4, like this. Okay. Also, we can by grounding this one, the member 3, we can achieve another mechanism. Or by grounding the member 2, we can achieve another mechanism. So therefore, this is kinematic chain. Kinematic chain. This is the mechanism, or let's say the model of kinematic model mechanism. So from the kinematic chain, we can derive as much mechanism as many as the number of the kinematic of the links of kinematic chain. Okay, so then let's continue after explanation that. So we said this is driver. What means driver? Why driver? So this is the smallest or shortest link. So driver means we drive, we rotate. Let them rotate with the angle theta, counterclockwise. And if the driver starts to rotate, so, and you can easily imagine, so this point, this is, let's say this point we call A, and this is B, and this is C, and this is D. So now we will later analyze the motion. We will later analyze the position, motion, so position, displacement, motion, acceleration, and the forces. So this is not just let's say the simple issue, because we use in the machines many mechanisms. So, and they are interested to solve several problems regarding the mechanism used in the machines, like position, displacement, velocity, acceleration, forces, and so on. And therefore, we go step by step in that direction. So at the end, we will be we will be able to make a necessary calculation. Okay, so then if I derive this one, so you can easily see the point B is point B undergoes the rotational motion or circular motion around the point A, and the point C also around D make circular motion like this, and this we call follower. Follows the motion, follower. It follows the motion. This is driver. This is the coupler which couple the driver and the follower together. And if we start to drive the mechanism in that direction, so the coupler is the say the couple the point B and C, and the follower has to follow. I mean, goes in that direction. In many applications, driver is a crank. That means can turn 360 degrees. That means full revolution. have full revolution, and the follower not full revolution. Let's say moves between two limited position, to limit position, like this. Huh? And the coupler undergoes the planar motion, and the driver undergoes the rotary motion, and follower also the rotary motion, but the coupler undergoes the planar motion. Planar motion means, in that sense, rotation and translation at the same time. That means relative motion. So we actually discuss this topic in dynamic. So you should remember, and if not, you should work on that. So we will use it here. Okay, let's continue. So regarding the 4-bar mechanism, so there are types of 4-bar mechanism, as I mentioned it here. So depending on the grounded member. So here we have crank rocker mechanism. That means this is let's use the laser pointer. Okay, this is the crank here, rotate like this, fulfill the circular motion, and the follower also fulfill the circular motion, semicircular, let's say so, and the coupler in between fulfill the planar motion, and this we call during the crank moves 360 degrees, that means full rotate, and the rocker, I mean the follower, undergoes the rotary motion in a certain limit. So therefore we call it a rocker, and this is crank, and it means the coupler always. So if we fix the member 2, I mean the crank here, you see that here, we fix the crank, and then we have 2 crank. So that means the crank and the follower are rotating, fulfill the full rotation, and this the crank is rotate, let's say in the circle here, the point, and the point we said D here, this rotating on this circle. So crank mechanism. And here we have rocker. None of them can fully rotate. And here 2 of them, I mean this one and this one, can fully rotate. Here fully rotating part is this part, and this is this not, they cannot full rotate, can rotate between 2 limited position. And here we have we have a different situation. That means that these 2 members, none of them can fully rotate, can, let's say, they fulfill the rotation in between limited position. So another mechanism is, so instead of here we change the member, the follower, and instead of follower we create a sliding link like this here. So then we have crank slider mechanism, we call. So this crank slider mechanism is very famous. We use it in internal combustion engine. So all internal combustion engine has this mechanism. So crank slider mechanism. So we have 2 types of crank slider mechanism. Inline, that means the points are on the same line, like this. Let's show it here. So on the same line. You see, on the same line. Huh? So there is no distance in between regarding or comparing to the base. But here, offset crank slider mechanism is not the same. Like this is like this here. So there is a distance in between. Huh? So therefore, we said offset sliding link or offset crank slider mechanism. Okay, the slider, crank slider mechanism, inline or offset, as I mentioned, has many applications in compressor, for example, piston compressor. This type of mechanism used, or in internal combustion engine. It's very famous since many years. Since the invention of the internal combustion engine. But the link in between coupler is always, we call it coupler. Here the turning part is the crank, turning in that way counterclockwise here like this. So counterclockwise crank, also here crank. And here this we call sliding link or slider. This is slider here. This part we call slider, and this is slider link. Actually, this is also here closed from that point. So this is also here closed. Okay. So those are the types of 4-bar mechanism. So regarding the dimension, so the geometry and dimension, I mean here, let's say this is the L1, the length L1, this is the member 1 here, and this is, let's say, L2, length 2, and this is length 3, and if we use these ones, for example, so length 4, length, oh, it seems not nice. Let's correct it. So length 4, okay, 4, and this is length 3, and this is length 1, and this is, sorry, 2, and this is length 1. So in order to draw such a mechanism, you can easily observe that we need the dimensions of this link. We need, if you know the dimension, so we can draw it. If you don't know the dimension, we cannot draw it. So it is really very strong involved in the geometry. Okay, regarding these lengths of the links, we can make some definition according to the Grashof criteria. So this is the Grashof is the guy who made research about. So there is 5 possibilities, 5 cases. One of them, the smallest link and longest link plus smallest link plus longest link must be less than the next 2. I mean P and Q we call this. We can say here, moment, maybe I have drawn it here and then show on that picture. So this is the small one. Let's say this is the small one. Okay. And the grounded. Small one. And this is the long one. And then let's say we have this here. So this is the small one. Smallest is the longest. Here, longest. And this could be the rest, this P and Q. This is, let's say this is the P, and this is the Q here. Dimension, the dimension, length. So if smallest and longest, total of smallest and longest less than P and Q, P plus Q, then this frame double crank. That means we have this one, double crank. So we achieve such a mechanism. And if smallest plus longest less than P and Q, we can also the shortest link must be the side. So this is shortest link must be frame and the side. So we can achieve crank rocker mechanism. If the smallest plus longest smaller P and Q, and the shortest link is coupler, and then we have double rocker. And if smallest plus longest is equal P and Q, P plus Q, any can be shortest link. So then a change point, we achieve change point mechanism. Change point I will show you. So change point, maybe do we have here? No, we don't have here. Okay, later I can show you change point. So if smallest and longest bigger than P and Q, the n of the shortest could be n of them shortest, then we have triple rocker. Triple rocker, that means this one here, rocker. So you see this dimension regarding the links are very important. Which type of mechanism we need in the machine and how can we arrange the dimensions and what are the constraints and what should be considered regarding the type of mechanism if we want to let's say change the dimensions. Okay, let's continue with the planar motion. 4-bar mechanism we discussed enough. The planar motion. So we have here, you see a mechanism grounded. Here you see grounded and the grounded. We have here the rotation. Here sliding. So let's check it, the degree of freedom. So anyway, when you have any, let's say the problem to solve regarding the mechanism, first of all, you have to check the joints and the links and the degree of freedom. All of them are very important because you have to be sure that the mechanism is it can run. So here we said this is the member one, isn't it? Member one. Okay, this is also member one. So the grounded part is always one. We say Grounded is the one. Grounded one. So then this is 2 here. You see, this is 2. It seems this is the crank, full rotate. And this is coupler here, 3. And this is 4 follower, like this here. You know, this is a 4-bar mechanism here. You can easily see. This is a 4-bar mechanism. 4-bar mechanism here. Or I can draw it like this. So this is a 4-bar mechanism. So this is a 4-bar mechanism. And you see, there is another 4-bar mechanism here. But there is another 4-bar mechanism. No, we cannot say 4-bar mechanism. Okay, this is not actually. So it is expanded. So this is also another 4-bar mechanism here. So another 4-bar mechanism. And this is another 4-bar mechanism. That means if we have such a driver here, so, and this is also another 4-bar mechanism. Let's take it out. So well, I will remove it and I will check the degree of freedom. So we said this is 4, 3, okay. And this is 5, you see here, this is the 5. And this is 6 here. And this is 7. And the slider is 8. Slider is 8. So it seems that we have a 6-bar mechanism. That means we are not, let's say, limited with the links. So 4-bar mechanism is minimum. And after 4-bar mechanism could be 5, 6, 7, 8, 9, 10. But if we have many links connected together, so you can imagine it is getting complicated, very complicated. So therefore, as simple as possible, we can solve many problems using the 4-bar mechanisms, or 6-bar or 5-bar mechanism. I would say till now I was involved in certain research and development, and I have experienced that the maximum 8 is enough. But not always. I mean, if you have, say, the different, so if you want to have different solution, if you want to solve quite complex problems mechanically, so then maybe you have to develop a new mechanism consist of several members or links. Okay, so we have seen that we have 8 members. That means n is equal 8. Okay. So the joint, we have all the joints are 1 degree of freedom. That means revolute or prismatic joint. Here we have prismatic joint, as you see here. So let's use another color here. So this is here between ground and the 8. This is the prismatic joint, and here we have pin joint, that means revolute joint, also here revolute joint, here revolute joint, here revolute joint, and here also revolute, grounded revolute joint, grounded revolute joint, and grounded revolute joint, and also here revolute joint. So, and here also revolute chain, but we have to be careful about. So we have here multiple joint. That means two members are, or two joints are connected. Two links are connected together. So let's let's see how many joints we have with 1 degree of freedom. That means joint primary. So here we have 1, 2, 3, 4 grounded. Okay, 4 grounded. And here we have 5. Here, let's use the laser pointer. Maybe you can see much more easier. So 1, 2, 3, 4 grounded. And these 3 of them rotating grounded joint, and 1 of them sliding grounded joint. So 4, okay. Then here we have 1, 5, and here the prismatic, revolute joint 5, revolute joint 6, revolute joint 6, 8, revolute joint 8, and 9. So here's a mistake. 1, 2, 3, 4, 5, 6, 7. 8, 9. Actually 11. Because it's 2. Okay, let's check it. Let's have the column. F is equal. F is equal 3 times n minus 1 minus 2 joint primary minus joint higher order. So if we say we have L is 8, so 3 times 8 minus 1 minus 2 times joint 10 and this is 0. Here we have 7, 3 times 7, 21, and here 20, so it's equal 1. So that means F is equal 1. Okay. So degree of freedom of the system, degree of freedom of the mechanism is 1. So it works. So if I start to turn here, so it moves, and this also moves, and we translate this motion and move, and this also moves. So okay, the 1 degree of freedom. Okay, let's have another example.
Doctor,
Yes.
the previous one, is number 8 also a multiple joint?
Number 8?
Yeah, because
Here, you mean this one?
Yes.
Yes. This we have, this this is also 1 degree of freedom. multiple joint.
Okay, thank you.
Actually, in some cases, we take it two, because three members are connected. There's two connections here. One of them is, for example, 3 5, and the other one is the 3 4, or 4 5, or 3 4. So there's two joint with 1 degree of freedom. But there are some, let's say, some exception in the mechanism, and you will see in some cases we have 0, but and degree of freedom 0, but the mechanism is can run. I mean, so some exception, and we will talk about if we deal with them. This is multiple joint and considered as 1 degree of freedom.
Understood.
So, okay, another planar motion mechanism. For the planar motion we have here. So this is also grounded. Let's use the red one. So the grounded here, you see grounded. Okay, here also grounded, and here also grounded. So this is one. We say the grounded is 1. So the 1, and this is 1, and also here the 1, the link 1, and this is here 2 and 3, and this is 4, 5, and 6. This is 6-bar mechanism. So 6 bar. So we have 6. Let's say n is equal 6. So the joint primary. So how many joint primary we have? Let's see. 1, 2, 3. Use this as a pointer to show it. So 1, 2, 3, 4, 5, 6. Okay, 6. So then we have to write 6 is equal 6. And a joint higher order, we have 1 here. This is joint higher order. So that means joint higher order is equal 1. So if we write the equations, so here is joint higher order. F is equal 3 times, and bracket, the member is 6. 6 minus 1 minus 2 times 6 minus 1. So then it is here is equal 15 minus 12 minus 1. Sorry. So instead, the higher joint 1, but it has 2 degree of freedom. This has 2 degree of freedom. So then we have to write here 2. So is equal 14, 15 minus 14 is equal 1. So does it move? Does it not move? So according to this explanation is degree of freedom 0, but let's see, 1, 2, 3. This, yani he is taking 7.5. Actually, 7.5 is not 7.5 is not usual. So this connection, this joint here, one point is calculated 1 point. We have here the 6. Okay, 6, 1.5, 1.5. So this has also special mechanism as an exception. You see here linkage with full, half, and multiple joints. So we have multiple joints here, and half, and here, and with full, and so on. So in these type of examples, you see the equation doesn't supply the sufficient results. So actually it works because it moves but degree of freedom is 0, and this joint here considered as 1.5, half, 1 and half. So we have six members, and normally if we use the equations, it makes 15 minus the, normally we have 1, 2, 3, 4, 5. Okay, we can take it as 2 here, multiple joint here 2. Yes, then we can 7. So maybe in that direction. I mean, this is a exceptional situation. We can consider this joint as 2 of the degree 2 joint. So if it is 2 joint, then we take it here 7. But if you take it 7 here, 7, that makes it 14. 14 minus, we have here also 1, the fifth. So let's do it in that way. Some mechanisms are so interesting, developed. I mean, we have the equations doesn't work very well. So we've said the joint primary is 6, but if we consider this link here, joint, this is actually 2 joint, and then if we because 3 members are connected, 3 links are connected here at multiple joint. So here 1, 2, 3, 4, 6, and one of them here 7. So then if you say 7, okay, 7 here instead of 6, 7, and so on. This is 1 here, okay, because we have here 1, higher order. So then if we write the equations, f is equal 3 times n minus 1 minus 2 times joint primary and minus joint higher. So then if we put the values, the numbers into the equations, so f is equal 3, n is n bars, and how much? N is equal 6, okay. 6 minus 1, and then minus 2 times 7, and minus 1, we have 1 higher order, the joint higher order, 1. So then is equal, here we have 15, 6 minus 1 is 5, 15 minus 14 minus 1. So at the end, we have 0 here. This is the correct calculation, actually. Correct consideration and correct calculation. So, and then degree of freedom, f is equal to 0. But if sometimes, even if the degree of freedom of total system is 0, it can be that it works. It moves. Okay, this is the correct way of calculation. So these multiple joint we have to consider as 2 primary joint, because 3 links are connected here to each other, and here is the higher order 1 joint of higher order. Okay, so regarding the connections or joints of the members, we have some definitions we use in the machines or the technical systems. These we call mechanism. Joint here, you see she grounded, sorry, here, grounded. One of them is grounded. This is mechanism. And degree of freedom is 1, +1, not minus, +1, okay. And this we call structure. Degree of freedom is 0, doesn't move. Degree of freedom is 0. We can easily calculate. Is it like this? F is equal, so 3 times the member, link 1, 2, 3. 3 minus 1 minus how many joint primary we have? 3. 1, 2, 3. 2 times 3. So, and here we have 0, and it is equal 6. Here 6 minus 6 is equal 0. So, it is also seeable that it doesn't work. It cannot move. So we call it structure. Degree of freedom is 0. And here we have degree of freedom -1. -1. And this we call preloaded structure. This is structure. This is preloaded structure. That means there is a load in between here. So, because of the deformation, I guess. So I think this is enough for today. So next week we will continue. And maybe special, before we come to the special mechanism, I'd like to explain this table also. So we have 4-bar mechanism, 6-bar mechanism, 8-bar mechanism, and so on. So this is the number of the bar, or the number of the bar: 4-bar, 6-bar, 6-bar, 8-bar, 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 and so on. So binary link and ternary link, quaternary link, and pentagonal or hexagonal, and so on. So depending on the type of the links, so you can create a mechanism. So the binary you can use for the 4-bar mechanism. You can use 4 binary link. And for the 6-bar mechanism, one type, we have 2 types. One type you can use 4 binary, 2 ternary, and the other tips 5 binary, 1 quaternary, and so on. And for the 8-bar mechanism, we have 1, 2, 3, 4, 5 possibilities. One of them, we use 7 binary and 1 hexagonal, and another one 4 binary, 4 ternary, and finish. So then the next one, 5 binary link, 2 ternary, 1 quaternary, and the next one, 8-bar mechanism, 6 binary, 2 quaternary, and this is also finished. And the next version of the 8-bar mechanism, 6 binary, 1 ternary, and 1 pentagon. Okay, then we will continue next week, special planar mechanism. And you will see what means. Sometimes we have degree of freedom 1, degree of freedom 0, and what's happened, and so on. And you will see these equations doesn't supply always. I mean, the result is okay, but we have some exceptional mechanism. So thank you for today.
Thank you, Professor. Bye.
Thank you,
Okay,
Professor.
bye.
Have a nice day.
Have a nice day. Bye.
Professor,
Yes,
what is the percentage for the midterm and the final again?
25.
For the midterm and 75 for the final?
No, we have midterm, we have homework.
Ah, okay. What is it? Oh, okay, I got it. Thank you.
Okay?
Yeah, okay. Have a nice day.
Have a nice day. Bye.